So the topic we'll be discussing in this lecture is swapping. So a process should be in the memory while it is executing. But sometimes a process can be moved out of memory temporarily. A process can be swapped out of memory temporarily to a backing store. So that process is called as swapping. Backing store can be a fast large disk which can store almost all the contents of main memory. Okay, so why swapping to be done in the sense for various reasons, like uh, maybe a high priority process may be coming, so there may not be sufficient space. So one of the process will be swapped out and another high priority process will be swapped in. Okay, the process that is moved in to the main memory, that is called as swapped in, and the process that is moved out of main memory, that will be called as swapped out. Okay, and swapping will increase the degree of multiprogramming. Okay, by swapping, degree of multiprogramming can be improved because now the total physical memory space of all process can exceed the physical memory that is available in the memory. The physical memory of the RAM of the main memory may be limited, but the number of processes that you want to execute may be more than that. That can be done by swapping. One is you need not keep all process in the memory. You keep only limited process in the memory, and depending on the requirement, keep swapping. So the degree of multiprogramming is achieved. Otherwise, keep all process in the memory, but don't load all process completely. Load only that part of the process which is required. So by that way also we can ensure multiprogramming. Okay. So the terms rollout and roll in are used in the context of swapping. So basically the lower priority process will be swapped out, and that is it will be moved out of the main memory, and the higher priority process will be swapped in. So swapping out is called as rollout and swapping in is called as roll in. And if we observe in the process of swapping, the majority of the time will be spent in transferring the content from main memory to the backing store, or from backing store to the main memory. So the total transfer time is directly proportional to the amount of memory swapped. So the total swapping time is directly proportional to the amount of memory swapped. So we should be very much specific in choosing the right process for swapping. Because if you choose a very big process for swapping, then you may have to spend a large amount of time in swapping itself. Because that because swapping depends on transfer time. A major part of swapping is in transfer time, and transfer time depends on the size of the file. Transfer times depends on the amount of memory or the content what you are going to swap. Okay. So as we already know, the system will maintain a ready queue which will contain the list of process that are ready to execute. So we have discussed this in CPU scheduling. There will be a ready queue which contains a list of process that are ready to be executed. So when the next process to be executed, the dispatcher will come and check whether that process is available or not. If the process is available, then that process will be allocated to the CPU. If the process is not available, if the process is not available, then that process should be moved from the hard disk to the main memory. So the dispatcher is checking one particular process whether it is in the ready queue or not. If the process is currently not in the ready queue, then it should be moved from the hard disk to the ready queue. But for moving from hard disk to the ready queue, there should be sufficient space in the memory. There should be sufficient space in the memory. If there is no sufficient space, then it should be swapped. Then it should be swapped. Then the operating system will pick up a process which is of least priority, and that process will be swapped out, and this new process will be swapped in. I think it's clear. So we have the ready queue. The ready queue will have the list of processes like process 1, process 2, process 3, all those things. And then the dispatcher will come and check whether a particular process is available or not. If it is available, it will assign to CPU. If it is not available, then it has to be loaded from the uh, hard disk to the main memory. But if there is no sufficient space in the main memory, then one of the process should be swapped out and the new process should be swapped in. Okay. So so as we have already discussed, this swapping, the most of the time in swapping is spent in move, moving the process, moving the process from one place to another place. Okay. So there the most of the time will be spent. That is in the transferring the content from main memory to hard disk or from hard disk to main memory. Okay. So, or backing store. So let us assume that we want to swap a 100 MB process. Let us assume that we want to swap a 100 MB process and the transfer rate is 50 MB per second. We want to swap 100 MB process. That means there are two processes, say P1, this is in the backing store, and there is another process P2, this is in the main memory. Okay, and these two processes each occupies 100 MB. P1 occupies 100 MB, P2 occupies 100 MB. Now it should be swapped. P1 should be brought to the main memory and P2 should be brought to the backing store. Okay, and the transfer rate is 50 MB per second. So how much time do we require to transfer one file, to transfer one process, to transfer P2 to backing store? We need 2 seconds. To transfer P2 to backing store, we need 2 seconds because P2 size is how much? 100 MB. 50 MB can be swapped in 1 second. So to swap 100 MB, we need 2 seconds. Okay. Similarly, to swap P1 to move P1 to swap out P2, we need 2 seconds. Similarly, to swap in P1, again we need another 2 seconds because P1 also occupies 100 MB and the transfer rate is 50 MB per second. Okay. So totally we need 4 seconds. So swap out time is 2000 millisecond, which is nothing but 2 seconds, plus swap in time also the same. So totally 4000 millisecond, that is 4 seconds are required. Right? So this is there any way to reduce this? Is there any way to reduce the swapping time? Yes, swapping time can be reduced if the size of the process is reduced. Okay, say instead of swapping P1 and P2, or say that P1 P2 is not occupying 100 MB. Say P1 occupies, which is to be swapped in. P1 is the one that is to be swapped in. Say P1 occupies only 50 MB. Then then obviously the time will be reduced. You need not require 4 seconds. It can be done in 3 seconds itself. Okay, or if there is another process P3, or if there is another process P3 which is already in the main memory, and that occupies only 50 MB, it occupies only 50 MB. Now swap in and swap out both can be done in 1 second each. So totally we need only 2000 2 seconds or 2000 millisecond, right? So, so we have to identify the correct process to swap in, to swap out, so that the new process can be swapped in. Okay, because the time here depends on the transfer, how much time it is taking to transfer, right? Okay, and also now it means that the operating system should know how much size each process occupies in the memory. That information operating system should know clearly. Operating system should always be knowing like how much size each process occupies in the memory, because then only operating system can pick up the correct process for swapping. So how it will be done in the sense, whenever a process wants some extra memory, it should request the memory from operating system by using the system called request memory. Similarly, when it is relieving some memory, or when it is releasing some memory, it should inform the operating system through the system called release memory. Okay. So by that, what happens in the sense, operating system always knows the memory occupied by each process. So operating system can effectively perform swap in and swap out at least time possible. So if a process is swapped out, should it be swapped in back to the same physical address? That depends. That depends on the address binding scheme you use, and considering whether whether IO was previously done or not. Okay, it depends on several factors. Okay, whether before swapping, whether the process has invoked any IO operation or not, it depends on all these factors. So in the modified versions of many operating systems like Unix, Linux, and Windows, swapping is normally disabled. Swapping is normally disabled because it is a time-consuming task, and swapping will be done. So it is not always disabled. Normally, it is disabled. Swapping will be done only if the memory occupancy exceeds a certain threshold amount. Only if the memory occupied by the processes exceeds a certain threshold amount, then only swapping will happen. Okay. And again, if the memory demand is reduced, again swapping will be disabled. This is how the modified versions of operating systems like Unix, Linux, and Windows behave. That is, they generally don't swap. Uh, Only when the memory occupied by the processes exceeds a certain threshold, swapping will be done. And again, if the memory demand reduced, the swapping will be disabled. So here is a schematic view of swapping. So we can see this operating system, the set of processes, and the process that is moved out, that is called as swapped out, and the process that is moved in is called as swapped in. So here P2 is swapped out and P1 is swapped in. Right? So is there any other constraint for swapping? Yes. So there is one important thing which is called as pending IO. So if a process is performing or waiting for an IO operation to complete, at that time, generally the process should not be swapped, because if it got swapped during that time, then it may create some other issues. Say for example, this is main memory. Say here you have three processes, P1, P2, and P3. So this is P1, this is P2, and this is, and the last one is P3. Say P2 is performing some, P2 is requested an IO operation. P2 has initiated an IO operation. P2 has initiated an IO operation. That IO is going on. The IO operation is going on, whether it is a reading a file or writing a file or whatever it may be, it is going on. Now P2 is waiting for that IO to complete. Okay, the IO is not yet completed. Say assume that during this time P2 was swapped. So P2 is swapped out and some other process P4 came in. Some other process P4 came in. Now what happens in the sense, this IO is pending in between. So after some t amount of time, this IO will complete, and it will return the result to this particular location. But here actually now P4 is there, so it will create some, what do you call, some havoc. Okay, so to avoid such things, we should not swap a process which is currently performing IO operation, right? So how to avoid this kind of thing? There are two ways to avoid this. One is, the first method is never swap a process that is performing IO operation. First method is never swap a process that is performing an IO operation or that is waiting for an IO operation. The second method is transfer. Whenever a process want to perform IO operation, transfer that to kernel space. All Whenever an IO operation is to be done, transfer that to kernel space. What does it mean? What does it mean? So, so transferring an IO operation to kernel space or to operating system buffers. Kernel space is otherwise called as operating system buffers. It means what, in the sense, you are asking their operating system to take care of this IO. Okay. So there, so what we are discussing in the sense, if a process is performing IO operation and at that time, if it is swapped, then after IO operation, the result will be returned to that particular place or that particular location where previously that process was stored. But now some other process is in that location, so it may create some issues, right? To avoid that, there are two solutions. One is never swap a process which is performing an IO operation or which is waiting for an IO to complete. The second method is whenever a process want to perform IO, transfer that IO to kernel space. Transfer that IO to kernel space. So now if P2 wants to perform IO, let P2 transfer the IO to kernel space. It means P2 requires the operating system kernel to perform this IO. So now P2 is not directly doing IO. The operating system kernel is doing the IO. So operating system kernel will complete the IO task. Okay. And then operating system checks. After completing the IO task, it will not directly return the result. It will check whether meanwhile there is any swap or not. If there is no swap, it will return the result directly to this location. Okay. But if there is a swap, but meanwhile when the IO operation is going on, say if there is a swap, if P2 is swapped out and P4 was brought in, so no more P2 is here, P4 is here. In that case, uh, after completing the IO operation, the operating system will not return the result. It will wait. It will wait until P2 comes into main memory. Okay. So whenever P2 comes into main memory, then it will transfer the result. So that concept is called as uh, uh, moving the transferring the IO to kernel space. Okay. So right, fine, but this is also called as double buffering. So this process of what you call transferring IO to kernel space and then to IO device, so that process is called as double buffering. That process is called as double buffering, which may create some overhead, so it also has its own overhead, but these are the ways to avoid that, avoid it, and these are the ways to deal with process that are performing. These are the ways to deal with the process that are performing IO operation or that are waiting for the IO operation. Standard swapping is not normally used in modern operating systems, but modified versions were used, like whatever we have discussed in the previous slides. Most of the operating system, they will they will swap only when the memory is extremely low. Okay, otherwise there is no swapping. How swapping is done in the mobile systems? Generally, mobile system they don't support swapping. Okay, so now we are using smartphones. These smartphones don't support swapping because they use flash memory. So the space is, we don't have as much space as that of a computer. Okay, and there are limited number of write cycles. You cannot perform many write operations on this flash memory. So there is a limit on the number of write operations that can be done. After that it will become unusable. Okay, and also there is a poor throughput between the flash memory and the processors that are used in the mobile platform. Because of these reason, generally the mobile phones they don't support swapping. Then how it deals with the problem of if you want to open more and more app, then how the problem is done, how the problem is solved with mobile applications. So if you take iOS, whenever the user wants to add more apps, then the iOS asks other apps to voluntarily relinquish allocated memory. Okay. So if the user is opening more and more app, then it doesn't mean then it do mean that he's not using some other apps, but it is still opened. So the iOS will ask the other apps to voluntarily free some memory. Okay, if they are not freeing the memory, then it may close some application which is being not used. Okay, otherwise it will otherwise the iOS itself will reclaim the read-only contents, whatever the read-only content that were occupied by different apps like the code or other things, that will be reclaimed. Okay. Similarly, Android also terminates other apps if there is no free memory. Okay. So before terminating apps, Android may terminate some of the apps if there is low free memory, but before terminating any app, it will write the status of the app to the to the flash, so that whenever the app started again, it can start quickly. And both the operating systems, both iOS and Android, it supports the concept called as paging, which we will discuss later. Okay. So the this is how swapping works in mobile system. So basically, mobile system, they don't swap. Okay. Instead of using swapping, when free memory falls below a certain threshold, Apple's iOS asks applications to voluntarily relinquish memory. Read and it will do like read only data or removed from the system, and later it will be reloaded if necessary. Okay. And Android also does the same thing. If it does not support swapping, it may terminate process if insufficient memory is available. Right. So that's it about swapping. Okay. Fine. Let us stop here. Thank you.